Okay, good morning to all of you. Am I audible?
Yes, sir. Good morning, sir.
Yes, sir. Good morning.
Okay, so another 2 minutes we should be starting. So let me try to share my screen. Is the screen visible?
Yes, sir, it is.
Okay. Okay. So it's still visible, lecture 5?
Yes, sir. It is
Yes, sir.
visible.
Yeah. Okay, so let's begin. This is Probability and Statistics for AI. We are in the 5th lecture. And today's agenda is to look at some techniques, definitions, and proofs towards establishment of central limit theorem and hypothesis testing. Now, we started this lecture series with the question of why probability. Why should we worry about probability and its methods? And we should also remind ourselves that these lectures are supposed to be academic entertainments. So we go slow and do not leave anything unproven unless it is self-evident. Okay, go towards absolutely fundamental uh, questions and ask why something is true. So we started asking why probability. Why should we worry about probability while doing NLP, for example? And these are perspective lectures also. We not only delve into details, but we also paint a big picture and try to have a perspective as to why we are doing anything. So the world of NLP definitely, sat up and took note when a few milestones happened. And these milestones are paradigm changing. They bring in a completely new way of looking at a problem and doing things in a completely new way. So one of them is this 1988 paper by D. Rose, Grammatical Category Disambiguation by Statistical Optimization. So grammatical category is nothing but part of speech, and part of speech is a disambiguation issue because the dictionary categories are most of the time multiple. So bank can be verb as well as noun. The preposition above falls in all 5 categories. Okay, noun, verb, adverb, adjective, and also preposition. So this is a grammatical category question, and disambiguation is needed there. So the world took note of this paradigm change coming in, but it became all the more noteworthy when Jelinek from AT&T Bell Labs showed that part of speech tagging accuracy improves dramatically when you train a hidden Markov model with part of speech annotated corpus. There is absolutely dramatic improvement. Okay, and all these nitty-gritty work, maybe you can call it nitpicking, of sitting down with the corpus and thinking linguistically, looking at language phenomena and trying to create rules for what will be the part of speech at a current position, given the information of part of speech and words preceding the current position. Those became those became somewhat out of date and trivial in the face of this assault by data-driven part of speech tagging. So suddenly there was a realization that one could train a machine with examples of part of speech, and you get much higher accuracy. So this was a paradigm change and brought in a lot of hope. Though, as we go forward, we'll see that this is not exactly true when we go higher up in the NLP stack, when we do pragmatic processing, sentiment, emotion, and so on. Data-driven, no doubt, but we also need knowledge graphs, okay, rules and knowledge graphs. The other paradigm change happened in 1990, where there was this paper from IBM giving different models for alignment of words when you happen to have parallel corpus. So everything begins with a machine learned system of aligning words. Okay, Delhi is the capital of India. Delhi Bharat ki Rajdhani hai. Align capital with Rajdhani, Delhi with Delhi, India with Bharat. You use expectation maximization to build this alignment. And there you see the instrument was probability again. Okay, expectation maximization because you wanted to maximize the probability of observation. And what is the observation here? The parallel corpora. This is the observation. Okay, and we wanted to maximize this probability by finding out parameters that maximize this probability. What was the parameter? The parameter was probability of English word given the Hindi word, probability of Hindi word given the English word. These are the parameters. Okay, the dictionary mappings. Now, in 1990, this happened quite historically, we would say, because this completely again changed the game of machine translation. Again, in 2015-16, we see papers coming from Google where even statistical machine translation is pushed to the background with neural machine translation appearing on stage. It is an interesting question again that neural machine translation, what exactly did it change? Okay, what did it change? Statistical machine translation made use of probability to build word alignment to phrase alignment, to syntactic tree alignment. All paradigms of statistical machine translation came from a very simple step of word alignment. So what did neural machine translation exactly change? What was the paradigm shift when it came? Okay, so let me leave that question with you, and we would like to answer as we go forward. Again, probability is the framework on which this is built. So 1988, 1990, the whole of 90s is the rule of statistical approach, rule of probability on various NLP tasks. I'm talking from the point of NLP. This is the experience in vision, speech, robotics, everywhere. Probabilistic robotics also came late 90s. So why probability? We would like to remind ourselves, we meet every 2 weeks and some things are forgotten. So we have to resort to probability because at every layer of NLP, there is ambiguity, starting from morphology up to discourse, co-reference, pragmatics. So there are multiple options and we need a method of scoring those options. This is a very fundamental operation in our trade in natural language processing. At lower levels, the ambiguity is more tractable. As we go high up, do sentiment, emotion, etc., ambiguity becomes more subtle, more complex, which is why higher level NLP tasks are much more challenging. Now, one might wonder, what is the ambiguity in morphology? The ambiguity in morphology is feature, gender, number, person, tense, aspect, modality for verb. So will go is ambiguous because it is not clear who is going, I or you or we or they. Okay, that's not clear. So all options remain alive, unlike the classical rule-driven approach to AI, which looked at the world in a very black and white manner. Okay, this is true, this is false, possible, not possible. Probability says everything is possible. Okay, zero possibility is also a possibility, only the score is zero. Now, the relationship between probability and ambiguity is that it is a systematic framework to deal with ambiguity. Ambiguity means uncertainty, and uncertainty needs the instrument of probability to deal with. So all possibilities are recognized, but with different scores. So if I take this sentence, this bank gives high interest. Bank being a noun has higher score than being a verb because of the environment. So since we raised this question of SMT, NMT, what exactly did NMT change? I'd like to draw your attention to the BART, okay, language modeling system. And there my understanding is that bank has a pre-trained word vector. In the context, this bank gives high interest, its embedding gets modified. So that's what BART would do. It will give a different pre-trained embedding. It will give a different embedding for bank compared to the pre-trained embedding. Okay, so there is a change incorporated in the representation of the word because of the context in which it appears. Okay, so just think of this point: statistical NLP giving a score for bank being noun versus bank being verb, and BART model changing the representation of bank, that is the component values of bank, because there is a context in which bank appears where give is a word, high is a word, interest is another word, all of which are neighbors of bank. Okay, so do please take this question seriously. Namely, the question is statistical NLP will give different scores for probability of NN given bank and probability of VB verb given bank. BART embedding will change the component values. Okay, is there any relationship between these two methods of giving a probabilistic score and changing the embedding values? What is the connection? So do reflect on this. There is some essential difference between statistical NLP and neural NLP. Now, proceeding further, so that one reason. Okay, so Aman asks, BART embedding will change the component values. This point is not clear. Well, let me just say that this comes from word vector. The word bank created, the word bank will have an embedding of itself created from huge amount of corpus. Okay, so that is a pre-trained embedding. You get, for example, word to vec embedding, glove embedding, fast text embedding. All of these are pre-trained embeddings. Okay, they, to my understanding, they don't respect the exact context in which bank appears, or it respects all the context and thereby ends up respecting no context in particular. So the pre-trained embedding creates the word vector from all possible context in which bank appears. So no particular context is given importance. But in this context, this bank gives high interest. Bank is noun. Not only that, bank is also the financial institution, and it has the capability of granting loan. Okay, so those information which go associated with bank, they are supposed to be encoded in the embedding. Now, this encoding is very specific. Nikhil asks, is the voice breaking for everybody? Is my voice breaking?
No, sir. Not
No,
no,
sir.
No. Okay. And also, is the screen visible?
Yes, it's
Yes,
at
sir.
probability and ambiguity.
Probability and ambiguity, yes. Okay, so Nikhil's connection possibly has a bit of problem. Nikhil, you can disconnect and reconnect maybe. So this is what BART does. The embedding, that is the vector, gets changed. Okay, so we will deal with this as we go forward. Now, one reason for invoking probability is to deal with ambiguity and give scores to different options. A very concrete reason. Another concrete reason, amongst many, which we'll explore as we go forward again, is confidence in data statistics. And today, we would like to spend some time on this question, confidence in data statistics. We ask, can noun follow adjective? And what is more likely, noun following adjective or verb following adjective? So probability of noun given adjective, is it greater, or probability of verb being adjective, following adjective is greater? So this is expressed in terms of conditional probability. Probability of NN given JJ or probability of VB given JJ, which value is higher? Okay, and that value leads me to the language phenomenon question. What is more likely? Can noun follow the adjective or verb will follow adjective? What is more likely? So that we obtain by looking at a sample. Can we trust that sample? So we are trying to develop this question, answer to this question. Okay. So to establish this discussion, I draw your attention to probabilistic context-free grammar, which is again a very nice innovation in NLP, probabilistic context-free grammar. Context-free grammar existed, okay, and Chomsky's contribution to capturing language in a formal framework is just immense, okay, very, very noteworthy. Now, S goes to NPVP is the starting symbol. NP goes to DTNN, NP goes to NNS, NP goes to NPPP. These are three ways in which a noun phrase is expanded or noun phrase is constructed. It can be composed out of determiner and noun, or a plural noun NNS, or a noun phrase and a preposition phrase. The last rule is a recursive rule with left recursion. NP goes to NPPP. Now, out of these three, we see that probability values are 0.5, 0.3, and 0.2. The probability values must add up to 1. Of course, you might ask, where is NP being composed of adjective and noun? Okay, so this is only a segment of the language, and our world is this. Okay, this language constructs which are shown on the screen. Now, NP goes to DTNN, probability 0.5 means that 50% of the noun phrases are in DTNN sequences. So this is based on a sample of corpus. I have annotated corpus, namely the tree bank corpus, okay, tree bank corpus. And there phrases are marked, also the part of speech tags are marked. So the sky will be marked as the as determiner, sky as noun, and the whole phrase, the sky, will be marked as NP. You have data of this kind. And apply some simple counts, take ratio of counts, and you arrive at this probability. But see the claim. I'm not saying that noun phrase in tree bank corpus 50% of the time consists of determiner and noun. The sky, a boy, okay, an elephant. These are examples of determiner and noun. I'm not saying that it happens 50% of the time in tree bank corpus. My claim is much more. I'm saying that whole of English language, okay, in time to come and in the past and everywhere in Nigeria, in Bombay, in Shillong, everywhere where there is English spoken form or written form, Noun phrase 50% of the times is determiner noun, which is a extremely sweeping generalization. Okay, this is a claim about language, and anything that has happened in the language will happen in the language. So this generalization, am I allowed to do? Okay, can I really say about English language that 50% of the nouns are determiner and noun? What about the blue sky? That is not DTNN. Okay, that's why 50% is, but is 50% correct? Okay, so that is the question we are asking about English language. English language, not about tree bank corpus, but based on tree bank corpus. So what is the justifiability of going from particular to general? When can I say there is validity to this leap of generalization based on observation of instances? Okay, so that is my second goal, which is confidence in the data statistic. And here probability gives me a way of building that confidence. So that is the second question. First question, you remember? First question is how to give a score to multiple possibilities in ambiguous situation. And these two questions, of course, are not dealing from each other. So, our question is obtaining and trusting statistics. So probability of NP going to DTNN is 0.5. And how did I get these statistics? We took samples of corpora and recorded the observations, or took a large sample and recorded the observation. So look at these two questions carefully. Am I audible? Everybody able to hear me?
Yes, sir, you are audible. Yes.
Yeah, and
Yes,
also the slides are visible.
Yes,
sir.
Okay. So look at the two questions, and we want to know if that is valid. Okay, if that question is valid, and is there equivalence between these two questions? So one question is, took samples of corpora and recorded the observations. That is the way I get 50%. And the other way of asking this question and answering it is, took a large sample and recorded the observation. So are these two methods of obtaining statistic valid? Okay, this is the question we ask. So taking many samples of corpus, okay, and recording observations, here we are changing the sample. And taking an extremely large sample and making the observations out of these. Are these two questions equivalent? Okay, that's an important and interesting point. Okay, so 1,000 samples of 10,000 words each versus 1,000 into 10,000 words single sample. Will both of them lead me to the same conclusion? Okay, so now we go ahead and try to answer this question. So the probability mass function for this rule, noun phrase going to determiner noun, probability mass function, is shown in this chart. Okay, look at this chart here. The probability range from 0 to 10, that means noun phrase expanding as determiner noun, that has frequency 10. Okay, in 10 samples, I found the probability of noun phrase going to determiner and noun only between 0 to 10%. In 45 samples, I found that probability to be in the range 11 to 20. In 101, 21 to 30. In 330 samples, 31 to 40. In 623 samples, 41 to 50. In 650 samples, 51 to 60. And then again it goes down. So I do see a bell-shaped curve emanating. So this is such an interesting and important point, okay, that the distribution of NP going to DT and N, okay, I still don't know, okay, what distribution it follows. Okay, I don't know, but a particular value, that is 50% is seen in large number of samples, and this behavior has a bell-shaped curve. Okay, I hope I am making my point clear. Okay, so this distribution is bell-shaped, though the distribution of NP going to DTNN in the actual data need not be bell-shaped. So I hope you are seeing the point. The point is that I do not know the underlying distribution, but a particular statistics must have a particular value inside the corpus, inside the population. And if I take samples, then that true value, okay, that true value, which I do not know, but I know it exists. I do not know the true value, but I know it exists, will have a bell-shaped behavior around that true value. This allows me to go from any distribution to normal distribution and allows me to pick the instruments of normal distribution for my inferences. So let me repeat this last statement. Note the breach in transiting from any distribution to normal distribution. Note the breach, okay, the connection. And note also the power that I derive after entering normal distribution and making use of the machinery of normal distribution. Okay, making the machinery of normal distribution. Making the there is some true value inside the corpus, and other values hang around it in the form of a bell-shaped curve, and it doesn't matter what the distribution, actual distribution in the data is. Okay, so I hope this point you appreciate. Okay, it doesn't matter what the distribution is, but I can get a bell-shaped curve. Okay, so this is a very powerful instrument at our disposal, and we are going to make use of this. So so now coming to this point once again about the distribution of NP going to DTNN. Okay, so that distribution is actually multinomial trial and multinomial distribution. Okay, multinomial distribution. Why do I say so? Let's do a bit of mathematics here. Suppose events A1, A2, AK can occur with probabilities P1, P2, Pk, where P1 plus P2 plus Pk is equal to 1. So if x1, x2 up to xk are random variables respectively, given the number of times that A1, A2 up to AK occur in a total of n trials, so that x1 plus x2 up to xn equal to n, then probability of x1 being n1, x2 being n2, xk being nk is equal to n factorial divided by n1 factorial, n2 factorial, nk factorial, p1 to the power n1, p2 to the power n2, pk to the power nk. So let us not let's say scared by this kind of probability expression. It is intuitively very simple. So if you have k random variables x1 up to xk, then what is the probability that these random variables get values n1, n2 up to nk? So that is given by a very nice expression, elegant expression. You have P1, the first parameter, raised to n1, the number of times that outcome appears. P2 raised to n2, pk raised to nk. And it is multiplied by n factorial divided by n1 factorial, n2 factorial, going up to nk factorial. So that is quite intuitive. Okay. And the example for that would be the throwing of dice, which we can relate to. The random variable is the outcome of throwing a dice. So in coin tossing, we have 2 outcomes. In dice throwing, we have 6 outcomes, so more than 2 outcomes. So when the number of outcomes becomes more than 2, the trial is called multinomial trial. resonating with Bernoulli trial, which gives 2 outcomes, and the number of times a particular outcome occurs follows a multinomial distribution. If there are 2 outcomes, then it follows a binomial distribution. Okay, so Bernoulli to multinomial, binomial to multinomial. So here we have 6 outcomes. Now the probability of getting a particular outcome is a property of the random experiment. Okay, in particular, it is a property of the entity involved in the random experiment. So the probability of getting a 1 from a dice is the property of that dice. Okay, it is a property of that phenomenon. Probability of getting a 2 is the property of that dice. Okay, so similarly, the probability of noun phrase being expanded as determiner and noun is a property of English language. Okay, appreciate that point. The probability of noun phrase being composed of determiner and noun is a property of English language. So noun phrase becoming adjective and noun phrase being composed of noun phrase and preposition phrase, all these are properties of English language. Okay, and we are trying to handle these by the instrument of probability. And there is a correspondence between them. Okay, the analogy between dice and the noun phrase formation rule. In language, the random experiment is observing language phenomena. In particular, we are focusing attention on noun phrases. What is the composition of noun phrases? How do noun phrases appear? Okay, the corresponding situation in dice is the random experiment is throwing of dice. NP rule has 3 outcomes as shown in the screen. Actually, it has many outcomes. There are many ways noun phrases composed of, but for the purpose of discussion, now NP rule has 3 outcomes. Dice throwing has 6 outcomes. Probability of each RHS for NP rule is a property of the language. NP going to DTNN is a property of the language. Probability of each outcome is a property of the dice. Probability of 1, probability of 2, 3, 4, 5, 6 is a property of the dice. By observation of a language corpora annotated, we try to guess the properties as close as possible to reality. By observation, we try to guess the properties as close as possible to reality, even for dice. So do please appreciate the analogy between dice throwing and observing the language phenomenon in a particular language. In particular, let's say we are observing the phenomenon of noun phrase construction. Okay, so this analogy is nice. Okay, that the dice throwing and investigating how noun phrases are composed are analogous situations. Okay, this is a nice point. And the moment you see this, you can empower yourself with the instruments of probability. The instrument happens to be this: the probability of an outcome, the number of times an outcome happens, is captured by this probability expression. I'm sorry for the mistake. It is n1 factorial, n2 factorial, up to n6 factorial for the dice. Okay, so this is the instrument that I'd like to use. And how many times NP becomes DTNN is a multi-nolly distribution. It follows a multi-nolly distribution, and the count is multinomial distribution. Okay, so this point is clear. And now from there, I would like to know, well, it follows multinomial distribution. Now I want to know what is the probability of dice coming up with 1. This is P1. That is a property of the dice. And this property I can guess only by performing many experiments, large number of experiments. I cannot look at the dice and surmise that, yes, this probability of 1 is 1 by 4. No, I cannot surmise by looking at the dice. I have to perform that experiment. Okay. Similarly, I have to observe the language behavior, the corpus. Okay. And from that, I can surmise how many times noun phrase becomes determiner and noun. So this is the analogy. And now from there, if I have found some probability, how do I have confidence in that probability value? Okay, how do I have confidence in that probability value? That is the question we are asking. And we can tackle this question by making this observation that in the long run, I'll get a bell-shaped curve or a normal distribution for a particular statistic. Okay, I hope you see this connection. Okay. Now, if your question is, sir, why appeal to normal distribution? I know that it is a multinolly trial and multinomial distribution. Why go to normal distribution at all? Okay, you can get this P1, P2, Pk values from setting up this expression and performing experiments and making observation. You can do that. Okay, that is one part of the story. Other part of the story is how confident are you based on this calculation about the whole language behavior. That's a different question. Okay, so I have the instrument for getting these statistics, but do I have the instrument to tell me how confident I am? No. For that, I need to go to properties of normal distribution. So continuing with the discussion, the parse tree computation is done by an argmax computation. The best possible parse tree comes from maximizing the probability of the tree given the sentence. And it turns out that, okay, Aman asks, how does the property of normal distribution helps in generalization? That is what we are coming to. The interval estimate, then the confidence interval, 95% confidence, okay, 5% possibility of failure. Those things are obtained from instruments of normal distribution. So, so this is how we compute the best possible parse tree. And for this, we need the probability of a parse tree, because the tree that is most suitable is the tree with the highest probability. Now, what do you mean by the probability of tree? How do you compute it? We get it by the probability of the production rules, multiplying the probability of the production rules. And that happens because of various kinds of independence assumption: ancestor freeness, sibling freeness, okay, and stationarity property. There are three assumptions by which I can do it. So I need these probabilities. You see, just note this. I need these probabilities: probability of NP going to DTNN. I need the probability of VP going to VPP. These are my building blocks, okay, nuts and bolts, based on which I can find out the probability of a parse tree, and I can give a probabilistic solution to ranking a set of parse trees. But I need these building blocks. Where do these building blocks come from? They come from the corpus. And I better be confident of those building blocks to have confidence in the whole parsing process. You see? Okay. So it is a tall requirement. The whole parsing process must be valid, and my claim about the language should be valid. Okay. A question in humanities and social sciences about the behavior of the language, and a question in computer science, how to produce the parse tree and how to rank it. Okay, marrying the language and computation. This is what is NLP after all. So the normal approximation to binomial happens. That happens through N and P, the two values, the number of trials, and P, the parameter. Okay, I'll come to Samuela's question in a little while. Okay, so I noted your question, Samuela. Okay, so we for large number of experiments in binomial distribution and probability P becoming more than half, we can make use of normal distribution. Okay, so now we'd like to see what concepts we have acquired so far, and keep this main question in mind. I want to make claim about population, about the whole population. In particular, in NLP, I want to make claim about properties of language, let's say English language, Bengali language, and what concepts and instruments we have acquired on the way. One thing is that we looked at risk minimization versus resource utilization by way of motivating the discussion. And what is more pertinent to us is the interval estimate. There we, for the first question, risk minimization versus resource utilization, we took the bridge problem. Interval estimate, we took the sand pile problem. Okay. And there it was handled by a very important concept, Z score. Z score is a vital instrument for us. Let me just remind you about this. And interval estimate is all we need for the moment. Okay, confidence interval. So probability of NP becoming determinant noun is 50%. I want to make this claim with some confidence. So I want this 0.5 value to fall in a confidence interval. That's a 95% confidence interval. And what is it I should do? That is where we are heading. So the important tool in that direction is the Z score. So you'll recall that Z score is the score with respect to a standard normal distribution. Standard normal distribution is obtained from any normal distribution by subtracting the mean from the value of the random variable and dividing it by the standard deviation. Okay, and this is called the standard normal distribution. The area under the curve from minus infinity to small z is called the Z score. So just remember this. This was done in 2 lectures, minus infinity to small z. So this area under the curve gives me that probability of a value falling in the range minus infinity to small z. And Z score table also we know how to read. If it is a 2-digit value, then we read the row up to first digit. So if I'm interested in 1.96, then 1.9 row I will look up, and 0.06 is the column I'll look up. Their intersection gives me the value 0.975. Okay, so the Z score for Z equal to 1.96 is 0.975. That means the area under the standard normal curve from minus infinity to 1.96 is 0.975. And that I made use of to find out the 95% confidence interval. From minus 1.96 to plus 1.96, the area is 0.95 under the standard normal curve. And this is the so-called and very frequently used 95% confidence interval. And the instrument for this is Z score. Okay, so this is something we had done. And how do I use this for the bridge problem? So in the bridge problem, we have a kind of reverse situation. I'm interested in finding out a value for a particular quantity and not exactly a confidence interval. But by making use of the confidence interval, I will do reverse calculation and get the particular value. The value I'm interested in is the number of cars that can be simultaneously allowed on the bridge. Okay, and how do I handle this problem? It is very instructive, you would recall, but I would like to repeat this because this is the methodology which is adaptable by us also for our NLP. So the bridge breaks when the total weight on the bridge is exceeding the tolerance level. The tolerance is known to be a normally distributed curve. The total weight on the bridge is also normally distributed because the individual weights of the cars are normally distributed. So the number of cars that make the bridge unsafe is n unsafe, and each car's weight is normal with mean 3, standard deviation 0.3. And here we have to invoke the central limit theorem. Okay, so the sum of normal variables is also a normal variable. So this is a version of the central limit theorem. So the total weight is normally distributed with mean equal to 3n. N is the number of cars, and the mean weight for each car is 3. And the standard deviation is, the variance is sum of all the variances. So there are n cars. The variance is 0.3 square. Okay, 0.3 was the standard deviation. So for the total weight is normally distributed with mean 3n and variance 0.09n. And tolerance is also normally distributed with mean 400, standard deviation 40. So there are two normally distributed variables. Since the nature of distribution is same, they can be compared. So the bridge is damaged when W total exceeds W tolerance. That is, W total minus W tolerance exceeds 0. Okay. Now comes the mathematical skill, which is brought to bear here. Mathematical, it is totally mathematical skill. We have captured the phenomenon in the form of a mathematical framework. Okay, that is the modeling part. Now comes mathematical skill. So W total minus W tolerance should exceed 0. So I want it will exceed 0, but by how much? What I want is that value should exceed 0.1. Okay, no, not that value. W total should exceed W tolerance. I want to make a probabilistic statement about it. I want the probability of W total minus W tolerance being greater than 0 to be greater than 0.1. The probability of W total exceeding W tolerance should be greater than 0.1. So I can translate this into an English statement. If n unsafe cars at a time are allowed to be on the bridge, then in more than 1 in 10 cases, the bridge will break. So I want to now work backward from this mathematical framework and get the value for n unsafe. This probability of W total exceeding W tolerance being more than 0.1 is giving me a situation of more than 1 in 10 cases, the bridge will break. That is the mathematical expression. Now comes the mathematical operations. W total minus W tolerance should exceed 0. I subtract 3n minus 400 from both sides. So I get minus 3n minus 400. I divide it by root over 0.0n plus 1600 on both sides. So I'm dividing by the standard deviation and subtracting the mean. So I have on the left hand side a standard normal variable, and the right hand side is a quantity which is of interest to me. Okay, minus 3 and minus 4. I'm interested in n. And the left hand side I've turned into a z score. So notice the technical part of it, the mathematical operation and the skill involved. So z score should be more than minus 3 and minus 400 divided by 0.0n plus 1600. So when I do so, I want this z to be greater than probability of this z to be greater than 0.1. So I had got z on the left hand side. Right hand side is minus 3 and minus 400 by this quantity. The probability should be more than 0.1. So z being greater than v should be more than 0.1. The probability should be more than 0.1. So the area under the standard normal curve for z exceeding this quantity should be greater than 0.1. So now probability of z greater than v is equal to 1 minus probability of z less than v, because the z score table is always given in the form of less than, minus infinity to less than a particular value. So we want probability of z greater than v to be greater than 0.1. That means probability of z less than v should be less than or equal to 0.9. Now the z score value should be less than or equal to 0.9. Consulting the z score table, I find that that value is 1.29. So if z value is 1.29, then the probability from minus infinity to 1.29 is 0.9. So that is what I want. Okay. And then I have 1.29 as the z value. And I have the right hand side involving the unsafe number of cars, n unsafe. And solving this equation, I find n is equal to 117. So 117 cars, if they're allowed simultaneously on the bridge, then 1 in 10 cases, the bridge will break. I'm able to come to that conclusion. Okay, so what you should note is the technique of converting a situation where you can refer to the Z score table. Okay, and the confidence interval has been decided a priori by me as 0.1. So, so this is the conclusion I have reached. Now we come to the central limit theorem, which we have been using again and again in our discussions. So there are many equivalent statements of central limit theorem. It is called the crowning glory for probability theory, and it has relationship with law of large numbers. Law of large number says as n grows, the probability that xn is close to mu goes to 1. So this is the situation that is applicable to us in the beginning part of the discussion. Remember, we said the probability of noun phrase going to determine a noun is 0.5. Okay, so this has relationship or support from the law of large numbers. As n grows, the probability that xn is close to mu goes to 1. Now 0.5, noun phrase becoming determinant noun, that being 0.5, is that mu? Okay, we'll see that it is. And xn is what? Xn is np goes to dt nn. And the probability of np goes to dt nn being 0.5, that probability goes to 1 as the corpus size increases. Okay, and this is a claim about English language. We have to, of course, 0.5 is only by illustration. What is the actual probability of NP becoming DTNN? Okay, that we have to find out from large number of experiments. Now, here there is an interesting point of view. Linguists like Chomsky, okay, Saussure, and so on. Linguists, especially the Chomsky school, is not really happy with this probabilistic treatment of language. Okay, noun phrase becomes determinant noun. There is a definite value to it. Why probability? Why probability? How many times noun phrase is determinant noun? There is a definite value to it. But why probability? The probability is because of my ignorance. Okay, probability is invoked because of my ignorance, because of unknowability. I cannot see the whole language in front of me. I cannot see the whole language corpus. It is not at my disposal. Even if I could get the whole corpus, I do not know what will happen in future. Future is still unborn. I don't know. Okay, will NP be expanded as DTNN at the time? It will be, but along with it, many other ways NP will be expanded. So I really don't know. So I have a statistic in front of me, which is 0.5, and I'd like to give some credence to that. Okay, so the invocation of probability is because of observer's ignorance. Okay, no quarrel with linguistics there. No quarrel with people who study language phenomena. It is the limitation of the situation, the fact that the observations can only be so many, cannot be infinite, cannot be predicted for future, that probability is invoked. Okay, so I think two high-level concepts I have communicated here. One is probability comes in because of unknowability. Second, probability comes in because of ambiguity. Okay, a situation can have multiple outcomes, and the probability of an outcome is a property of the language. We move towards a good estimate of that property by performing many experiments. So there is no surprise there. We know intuitively that you have to perform many experiments. But how to give it a formal shape? I give it a formal shape in the form of X% confidence interval read from the Z-score table. And that is the technique that I'm using. Okay, so maybe I'll stop now. I'll show you the statement of the CLT, central limit theorem, which again is based on what is called the moment generating function and uniqueness theorem, Next time we'll definitely do moment generating function and uniqueness theorem in our pleasant way by appealing to NLP and machine learning. And this is the statement that if you take random variables x1, x2 up to xn and take their sum, okay, then take their sum, and each random variable has mean mu and variance sigma square, then Sn minus n mu divided by sigma root n follows a standard normal distribution. That is the theorem. Or in other words, the sum of random variables, all of which have same mean and same variance, that sum follows a normal distribution. Okay, this is not an intuitive statement. It's a big surprise, and that's why CLT is called the crowning glory of probability and statistics. That is not at all. Did you expect it that the sum of variables which are distributed, which have their own distribution but same mean and same standard deviation, their sum follows a normal distribution? Okay, if n is more than 30, that is I don't think not intuitive. Okay, that you did not expect. And please try to link this statement of central limit theorem to NP going to DTNN. Okay, how from central limit theorem I can have confidence in my observation, provided the corpus size is large. Okay, so that is where I leave you, and I have a few theorems in the form of variance, moment generating function, uniqueness theorem. Those are very nice. Those will be our conceptual tools next time. Okay, so there were some questions. Oops. Diptesh, what are the questions? Can you read them?
Sure, sir.
Yeah.
Aman asked that BERT embedding will change the component score. This
No,
line
this I
is not
explained.
clear, sir.
This I explained. Yeah, this I explained.
Okay.
Samuel has it. I can read that question now. If we understand it correctly, is it better to have large number of small samples instead of one large sample because it enables us to make use of the properties of the normal distribution? Not exactly, Samuel.
Okay.
Is it better to have large number of small samples instead of one large sample? No. I want to answer this maybe in the next class.
Okay. Right. Because when we looked at this property, right, that we have large number of samples, so every sample gives us some probability about that outcome, and that outcome follows the normal distribution as we saw it, right?
Yes.
So it looks like that we could use the power of normal distribution here, but yeah, maybe we'll understand it better when we go into more depth.
Right, more depth, and in particular, reflect on this question: to take many samples of fixed size, or take one sample of a very large size. Okay, so that is the question to think about.
Right.
Yeah. And how Sapan says, how does this relate to, say, 30-way cross validation? What is the question, Sapan? Sapan, can you hear me?
Yeah. So we basically talked about identifying our model parameter. Basically, what should be the
Yes.
probability for that rule?
Right.
So in the paper, many times we report our results. So there, one way people report is using these confidence intervals, and the other way is they report using cross validation. So in that context.
I see. So, by the way, these two are two different issues, and they do not compete with each other actually. So, so even if you do 5-fold cross validation, in cross validation for those who are new to NLP machine learning, in cross validation we'll take data and we divide it into, let's say, 5 partitions. We train using 4 partitions and perform test on the 5th partition. So this way you will have 5 different experimental setups. Okay, train with 4 partition and test on the remaining partition. So from that we compute the average accuracy value. and then say that my accuracy is, let's say, 72%. Okay, so but I mean, if you look at closely, this is not a confidence statement. Okay, we can always be asked at this point of time, what is your confidence in this 72%? And my answer cannot be that I performed 5-fold cross validation. I mean, we do so all the time. We do so all the time. Okay? And if that cross validation result is significantly more than baseline, significantly quote unquote, we have to make it formal through probability again, significantly. Okay, so appealing to confidence interval and normal distribution is brushed under the carpet of significantly. Okay, so the 5-fold cross validation is not really ensuring confidence, though we do so.
So, sir, let's say somebody does 10-way cross validation, and each of the fold they get the same value 0.5 for this rule. So, is it in some sense relating to this, like?
Yes. So if okay, if the number of, so are you saying that if the number of partitions get increasing?
Yeah.
Instead of 5-fold, if I do 30-fold and then the 100-fold, does it increase? Does it increase confidence in my values? So notice that as we increase the number of partitions, the sample size also decreases. Okay, so the size of the testing corpus decreases.
Right.
In 5-fold cross validation, it is 20%. In 100-fold cross validation, it is 1% of that corpus. So sample size decreases. So this brings us back to our the question that Samuel asked. Is it all right to do observation on many small samples, or is it better to make observations on small number of large sample size? So a large number of small samples or small number of large samples is the key question. Okay, so that we would like to answer systematically.
So, sir, one more question. So, in domain of applications, many times we don't have enough tag data. So, in such situations, what is the proxy for doing this exercise?
Come again, once again.
So, in domain applications, we don't have enough tag data. So
Okay.
in those cases, what is the proxy for? So let's say if we every time randomly initialize our model and it leads to good, I mean, same good accuracy, does it mean that our model is good, like in that sense?
So the dependence on accuracy on the initialization, that's what you're asking?
Yeah. Can that be a proxy for confidence?
Oh, good question. So if I initialize this very well, will I have more confidence? Okay, so I think you see the transfer learning does something like this, right? In transfer learning, I fine tune a parent trained model. No, so I have the parent data and I have the child data, child domain and the parent domain. The training is done on the parent domain, and I retrain using the child domain data. So I hope that my initialization is very good, and therefore the accuracy also will be very good. So your question is how to link the goodness of initialization with confidence, right? It's a good question.
Yeah, I mean,
I have to think about it.
Yeah, and little different. So, so for example, we have a little large pantry bank, but one of the data set that we have for material science, we have about only 130 papers. So now with such a small data, how do I do the exercise of identifying confidence intervals? So there, let's say if I learn my model 50 times, each time initializing the model parameters, let's say LSTM parameters differently, and if I observe the same good accuracy, I mean, can we relate these two things? Like, can that be treated as a way to identify confidence in our model?
I have to think about this. Can't answer this immediately. But good question, definitely. Yeah. So can I also say that you are trying to link confidence interval with efficacy of initialization?
Yeah, I mean, it will mean that, because I mean that's one way of doing it, and that's where initialization will come into picture. But I'm not sure whether there are any other ways of doing it when you don't have enough data.
Yeah, I need to think about it. I think it's a good question, Shirley. Okay, so any other question, comments, points? Okay, so we'll continue. Next week, next lecture, there will be two beautiful theorems: moment generating constructs, moment generating function, and uniqueness theorem. Okay, thank you.